The Field Robotics Center is researching navigation for applications such as material handling at construction work sites, mapping of hazardous waste sites, exploration of planetary surfaces, and off-road hauling. We have gained valuable insights from our earlier research into mobile systems such as the Workhorse, a teleoperated robot for nuclear accident recovery, and the Terragator, an autonomous terrestrial navigator. We have recently built the NavLab, a test bed for research in robot navigation, image understanding, and the role of human interaction with intelligent systems. The NavLab is a roadworthy truck modified so that researchers or computers can control the vehicle as occasion demands. As a mobile navigation habitat, it accommodates researchers and significant computing on board. Because it is self-contained, the NavLab is not subject to telemetry bottlenecks, communication faults, or dependence on stationary infrastructure, and can travel to confront navigation problems at a test site. The NavLab configuration consists of a chassis, drivetrain, and research shell. The vehicle chassis is a modified van with a computer-controllable hydraulic drivetrain. Driver controls allow a human monitor to override automatic control for overland travel, setup, and recovery from experimental errors. The NavLab shell houses all onboard equipment, including computers, controllers, telemetry, and internal sensors. In addition, it provides a working area for operators and allows researchers to gather data within the confines of the vehicle. Researchers can monitor and supervise the NavLab from the operator's console for setup, error recovery, and tuning. Interface modes include virtual vehicle instructions, joystick motion control, and direct servo motion commands. The console also incorporates several displays to show the current states of both the vehicle and control computer. The core of the NavLab is the vehicle controller. This multi-processor computer controls all locomotion, actuation, and physical sensing. It interacts with the computer host, inertial guidance system, and human operator to implement varying degrees of autonomy. The NavLab controller cues and executes virtual vehicle commands originating from a computer or human host. This command set provides high-level motion and control primitives that mask the physical details of the vehicle. The NavLab supports a choice of sensing to accommodate many types of navigation research. Video cameras provide color and intensity images for scene interpretation. Road edges, for example, are analyzed through intensity, texture, and color segmentation. A scanning rangefinder sweeps the surroundings with a distance-measuring laser that provides useful three-dimensional information about the geometry and reflectivity of the environment. Taken together, color, intensity, range, and reflectance data provide a rich basis for building natural scene descriptions. Sensor information from several sources can be fused to achieve more robust perception. A Blackboard computer architecture integrates the distributed processes that sense, map, plan, and drive. The Warp machine, a CMU systolic array supercomputer, is improving speed and performance benchmarks of the NavLab. The NavLab represents the continuing evolution in the design of mobile vehicles. Fully self-contained, the NavLab is a milestone in autonomous mobile robotics research.
It's December 12th, 1982. The temperature outside here in Pittsburgh is about 25 degrees. If my ears seem red, it's because I'm cold, not because I'm embarrassed. I'm Ivan Sutherland of Sutherland, Sproul & Associates. We're making a videotape report of our six-legged walking machine. This walking machine was built by Sutherland, Sproul & Associates in cooperation with the Robotics Institute of Carnegie Mellon University. The machine is under contract with the Defense Advanced Research Projects Agency Systems Science Office for experiments in the control of machines that move by means of legs. Our machine has 6 legs, as you can see, 3 on each side. The legs are numbered like the pins on an integrated circuit, counterclockwise from the driver's position. 1, 2, 3, 4, 5, 6. Each leg is moved by means of 3 blue hydraulic cylinders which are attached to it. The two upper cylinders in the V-shaped arrangement can cause the leg to move forward and back and up and down. The horizontal cylinder here moves the lower part of the leg in and out in order to make the machine move sideways. These red load cells are used to measure the forces on the legs. And there are position sensors in the knee joint and the hip joint which permit the microprocessor on board to measure the position of the leg. Power for the machine comes from an 18 horsepower gasoline engine mounted here, which drives by means of a V-belt 4 variable displacement pumps which are underneath the engine area. These variable displacement pumps cause oil to flow in the hydraulic circuits at a speed which is dependent on the setting of a control lever. There's a control lever here for one variable displacement pump and another control lever here for a second one, and there are 2 more control levers on the far side. These control levers are connected by means of these tubes which have hydraulic fluid in them to the driver controls, which are a stick and 2 foot pedals that the driver uses to control the vehicle in motion. Today we're going to use the foot pedals to control speed of motion and rate of turn, and because it's the first time that I've driven the machine using the foot pedals, we may have a little excitement later on when we actually run the machine. We're now on our 3rd version of the walking program. The first 2 versions used the legs in a fixed sequence. This 3rd version has 2 sequences of leg motion, one for the 3 legs on the right side and one for the 3 legs on the left side. When the machine is moving forward, the leg sequence uses the rear leg first, and then the middle leg, and then the front leg. When the machine is moving backwards, the sequence of leg motions is reversed. The way the machine works is that the driving rate of the legs on the left side and on the right side can be made to be different in order for the machine to turn. If the legs on the left side drive faster, the machine turns to the right. If the legs on the right side drive faster, the machine turns to the left, just like a tank or a bulldozer. 2 of the variable displacement pumps are used for that driving control, and the other 2 are used to control the legs while they're elevated or to control the motion of the legs while when the machine is moving sideways.
This machine was built with 6 legs in order to avoid the balance problem. With 6 legs, it is possible to keep 3 of them on the ground whilst elevating 3 of them to take the next step. We were surprised to discover that because the machine is large and quite massive, it is almost possible for a driver to balance on only 2 legs. We are encouraged to think about machines which use balance effectively to provide better walking control with fewer legs. We believe that a mastery of balance will be important to future walking machines.